Next, just to talk about this SOA record, this SOA record. This is really just saying the base configuration for this level of DNS hierarchy or this domain. You'll sometimes hear this referred to as a zone, almost as interchangeable terms, zone and domain, where I'm basically defining default timers for DNS servers and a serial number. This number is one of the only ones you really need to care about in this list. That number you will increment at least by 1 every time that you need to change any data in this DNS configuration, and that's going to be used as a reference to know how current your data is if you're a DNS server. So that one is important. Below that is you have name server definitions. So I'm defining first what DNS servers are authority for this domain. So this NS01 is the name of the DNS server. Again, there's no dot in this sentence, in this statement, which means it's implicit that it's really ns01.epc.mnc101 and so forth. And then I'm defining that an A record, an IP address for that server, as being 192.168.1.161. So this is kind of the minimal amount of information you can define about a level of DNS hierarchy. What name servers can give information about it, and how do I reach those DNS servers? That's what this is. So this part is generic for any DNS configuration, and now we're going to go back to our 3GPP scenario and show how we can meet the objectives of that scenario through our DNS configuration. So quickly to go back to the scenario again, we have 2 MMEs, 2 S gateways, 2 P gateways. We don't have any roaming, we're only GTP protocol, we have no compatibility issues, nothing like that. And we want to make the 1s active and the 2s passive. So to do that, we are going to define the MMEs and the S gateways under a tracking area, and we're going to define the P gateways as mapping, well, to a PDN, but really to the APN reference for that PDN. The 2 main types of records at a minimum that we're going to need is going to be those 2. So first, let's go to tracking area first. So all of these records here, you're going to see they are Network Authority Pointer records, or NAPTR, which is a different type of record than anything that I've discussed up to this point in the video. So we've talked about A records, what's the IP address of X. I mentioned MX and NS records, so mail server information and DNS server information. Network Authority Pointer records are very flexible records, and they're going to map services. I should put it this way. They have a few different uses. But in the context of the EPC, they're primarily going to be mappings of services to interfaces that can provide those services. That's kind of the way to think about it. So there's a few columns here like regex, but we're going to see that in use in a different scenario when we're talking about IMS. But we don't really care about that for the purpose of tracking area definitions and APN definitions. So to look at a tracking area number, this is how it will be configured. Remember, it does not end in a dot after TAC, so it's implicit that it really ends with .epc, .mnc101, .mcc101, and so forth. But I just wanted to show here that the tracking area number has a hierarchy in itself. So it says that the tracking, again, right to left for DNS hierarchy, tracking area code high byte 00, and then to the left of that, low byte 7B, which in hexadecimal would work out to tracking area number 007B or decimal 123. So I put a comment to write it in decimal just because people typically think in decimal and it's easier to write it that way and understand it. But the DNS hierarchy actually allows you to say that you could have TAC HB00 as one whole domain in DNS if you wanted, or in HB01 as a whole other domain. So that's just so you understand the notation of how tracking areas are written in DNS. And all of these statements here, NAPTR statements, they're information about services that can be that this tracking area has available to it. And there is a heavily standardized notation for these. So again, I would defer you to 3GPP TS 29.303. They define this notation for services, where I'm saying X3, it's pretty much human readable though. So X3GPP S gateway, so I'm saying that if you're looking for an S gateway, so if you're an MME and you're asking for this tracking area, what serving gateway can serve it, and what protocols does it support, and what interfaces does it support? Well, if you're looking for an S gateway, this record here is saying S gateway S5 interface GTP protocol specifically, as opposed to PMIP. If you want that, you can get it by talking to this interface on an S gateway, this topoff.bond1 100.sgw01. And if you want a same record, actually, same type of record, same service, you can talk to S-Gateway 2. Right? So S-Gateway 1 and S-Gateway 2 can both provide the same service, so it can provide the same service to the same tracking area. And the only difference really between these two records is, well, one, that they're talking about S-Gateway 1 versus 2, but also this order statement. And this is going to end up being priority. So priority 1, priority 2 is what this order statement is going to end up meaning for this type of record. So try S-Gateway 1. If that fails, S-Gateway 2. That's my order of preference. And that meets my requirement when I said that I wanted it to be active on S-Gateway 1 and passive on S-Gateway 2. This is how I'm accomplishing it. I'm doing the same here with S1MME and S10 interfaces, which are the 3GPP standardized S1MME and S10 interface names. So if you're looking for S1MME interface, if you're an eNode B that supports a network authority pointer record query, and you're looking for MMEs that can serve this tracking area, well, your first is this MME1. You can tell from this code number, and here you get a sense of the MME hierarchy, which is different than regular nodes. It's standardized, so .MME is a whole 3GPP standardized level of hierarchy in a PLMN. So MME group number 1, MME code number 1, so you have the GUMI, the Global Unique Mobility Management Entity identity of that MME embedded within the DNS hierarchy. And here he's got an interface called S1 and top off. Top off means something that I'm going to talk about in a little bit. Next, I have my records for the S10 interface. This is, depending on your use case, you probably do need these, depends. But S10 interface, so if I'm an MME and I need to learn about the other MME in this tracking area, you can query, and this is information about the MMEs in this tracking area, not for S1, but this is the interface information for S10. Now, you'll note in this configuration here, I put bond 0, 100, here I put S1. It's going to depend on what you want to call an interface on the system. So you might have, like in 3GPP's examples, they'll put like ETH0 if it's literally a Linux server with a network card with an RJ45 port with one Ethernet port with one IP address on it. You could actually map it to that. You might refer to just the idea of S1 and have that be a single IP address that it has some internal high availability within a node. You might have S1 address 1, S1 address 2, right? So there's entirely different ways you can write this, but just know that everything after MMEC1, again to the left, refers to an interface. And so same deal here, S-Gateway 01, well, everything to the left of it, this bond 0, 100, that's an interface on the node which is called SGW01. And again, because there's no dot, it's assumed that it ends with .EPC, .MNC101, .MCC101, and so forth. So that's what this tracking area number is doing. So I've defined ActivePassive with these order statements 1, 2, 1, 2, 1, 2 for the tracking area for all three types of services. And I'm doing something similar up here for Internet. For the Internet APN and a VoIP APN. So Internet APN I've defined, and I've said there are two types of two P gateway records that can support these services. XS5 GTP for the PGW, XS5 GTP for the PGW second row, and XS8 GTP for the S8 roaming interface. So I've actually done something I should not have done. I've added the S8 interface. That does not meet the requirements in my scenario, so to meet the requirements in this scenario, I'd actually have to delete this statement because I'm advertising S8 interface capability, which I don't want to do because my scenario, if I go back to my objectives, my requirements is that there are no roaming requirements, so I should not be advertising that. I included that actually, this was intentional, I intentionally did that just to sort of show how you can kind of navigate this and see how something might not be as you need. Advertising S8 versus not is an important thing for an APN because you're saying whether or not it should be globally outside for roaming or not. And these two other records are for legacy interfaces. So my requirements were that this be co-located, that this is also supporting PGate, or did I have that requirement? Sorry, I did not. I can remove that. That was a legitimate mistake. That was a legitimate mistake. So these two lines you could actually remove because I don't have a requirement to support GGSN interfaces. So I can remove those and simplify this APN configuration somewhat. And again, the way that I make this ActivePassive, all I'm doing is with these order statements 10 and 20, priority 1, priority 2, 10 and 20, priority 1, priority 2. And again, left to right, you see it's P Gateway 1 and P Gateway 2. They happen to have an interface of the same name called GTP-v2c. That's not standardized, I just made that up. And so it's pretty human readable in the way that I've written it here. I try to write it as cleanly as I can. And my particular install of Vim, the tool I'm using on my server to read this file, I've added sort of custom color rules so that you can sort of see it in a more readable format. Now you might be thinking, if you've got a lot of MMEs or a lot of P gateways or a lot of probably even more typical tracking areas, if you've got large numbers of tracking areas, you don't want to maintain all of this amount of data for every single tracking area. I mean, what if you have to change it, right? So the answer is you're right, you do not want to configure all of this for a tracking area. So one trick, I'm just giving you a practical example, one trick you can do, this tracking area name, this tracking area 2, so high bit 00, low bit 02, hexadecimal 2 is also decimal 2, tracking area number 2, I've defined a profile for it. So TAC profile 1, and then under TAC profile 1, I've defined all of my configuration for a tracking area. So if I had 1,000 tracking areas that were all I wanted to treat the same as having all of this configuration apply to it, I can define that here. So only a single statement saying, for this tracking area, apply profile 1, I end up aliasing it with all of this profile data. So I only have to define all this data once and assign all my tracking areas into the profile. You can use wildcards too, like you could say TAC LB0 star, or just star. So anything that starts with high bit 00, assume that it has, right? So you can enter it once for a range by using wildcards in DNS. I'm using a profile statement here with CNAME. CNAME is another type of record, which is really just an alias. I'm saying if he's asking for tracking area 2, he's really asking for tracking area profile 1, and so give him the information for tracking area profile 1. That's what this record would be. Next up is MME definitions. Here I'm defining two MMEs, MME 1 and 2, by their MME code numbers. And all I'm really doing for these is defining X10 or S10 and S1 service information. You might be thinking, well, wait a minute, if you convey and configure MME information in tracking areas, why do I need to define them in an MME configuration? And the reason is that depending on the call flow, there are times when you're asking what MMEs can do something for a tracking area. There are other times when you're asking what an MME, a particular MME that I know about, what it can do. Different types of records. So this is an MME record to answer that second type of question. These records in this TAC profile or in this tracking area definition answer the first type of question. If I know the tracking area and I want to know information about the MME that can serve it. And down at the bottom here, I'm answering the questions that were being begged above. So it's all well and good that I'm saying if I want to reach an S gateway that can serve S5, that I can reach S gateway 1 through its bond 0100 interface, but what's the IP address of that interface? Ultimately, I want to send that GTP message in an IP packet towards that S gateway. How do I do that? And that's where these records come in. These are just regular IP address records, the A records. So I've flagged that service as being mapped to this interface, and then aside from that, I've also mapped this IP address as being the address to use when I want to reach that interface. So these are A records. Incidentally, if I go back to all these NAPTA records, that flag statement says what to do next. Flag of A means ask for the IP address, or what you're really looking for is an IP address for this interface. We'll see S used when we're talking about you could use S here technically, but S would say that an SRV record is coming up next. U would mean URN, which is something different. So I mentioned that only to kind of illustrate that this notation is even, I say that A records are just scratching the surface of DNS, but this use case is just scratching the surface of what you can do with this NAPTR record type. It's very, very flexible. So node definitions, you may or may not need these. It is a good idea to add them. In a scenario like, for example, static APN definition to a P gateway, there are cases where an MME might directly need to query a P gateway by its name and not by its APN. In that case, similar to how we have MME definitions, you should be defining P gateways. S gateways, not so much. I'm not actually offhand aware of any scenario where you would have an S gateway by name queried, but P gateways by name queried can happen. Classic example would be static APN definitions in an HSS. There are certain types of mobility scenarios, especially when you're talking about use of trusted and untrusted Wi-Fi, or I shouldn't even say Wi-Fi, but just in general non-3GPP access, where a non-3GPP access network, which is pretty much synonymous with Wi-Fi, you can have cases where a system might know its name of a P gateway, but not necessarily have a reference, or use a reference, I should say, for an APM where it just wants to query the name. The formal name for that in 3GPP is called the canonical node name. So if I just quickly draw out a full name record for this P gateway, you've got top-off.gtp v2c.pwz02.mcc101.3gppnetwork.org. Well, the way that this works, this top-off is a special indicator, which we'll talk about in scenario 2. That is stripped off. This GTP v2c is recognized as the interface for the node, and then everything between this and EPC is understood automatically to be the canonical node name within that particular PLMN. And a canonical node name is kind of the formal name of the system itself, which it sometimes can be queried directly. So this P gateway PGW02 with this automatic implicit EPC.MNC whatever, that's actually the record that I have defined here. So if someone wants to query for the canonical node name of the P gateway, this is the query type that it would issue. So that is it for this zone file as it relates to scenario 1. And then quickly to go back, we've got MME1 prioritized for all the services we're advertising for it, SGateway 1 prioritized over SGateway 2, PGateway 1 prioritized over PGateway 2. And now I'm going to exit this zone file, and we are going to move to the other zone file and the other scenario. Now here we have something much more complicated. This zone file, we have a total of 6 P gateways and 6 S gateways in our administrative control for our PLMN. We have really what I've drawn here as 8 greens in 2 different regions. So this is like I said, intermediate. So we have a west region and east region. We want our S gateways in the west region to map to our P gateways in the west. We want east to east. We want west to be able to talk to east and vice versa on failover scenarios. And then last resort, we want these yellow P gateways and S gateways to be used if the greens fail. At the same time, we want to prioritize the yellows for roaming. So here's the objectives altogether. So load balance between S gateway 1 and 2 in a local region for a tracking area. If that fails, load balance from this tracking area towards S gateway. So this is number 1. So this is option 1 for the tracking area. Apologize if this is a little bit unclear. This is option 2 for the tracking area, right? And then if that fails, use S gateway 3 in local region. So this is option 3. Oh wow, that's a terrible 3. This is option 3 in the local. And then option 4 is going to be to use S gateway, yellow S gateway in the opposite side of the network. So prefer the greens. So prefer your closest greens, then prefer the far away greens, then prefer your closest yellows, then prefer the far away yellows. That's what I'm trying to achieve for the S gateway. Now for roaming on the S gateways, I want to load balance between the 2 S gateways, which are yellow, regardless of region. And that this may or may not be a practical scenario. I'm really just, the whole point of this scenario, I'm just sort of throwing out different types of DNS requirements that you might have for a network, and then we can go over how we're going to achieve all these requirements, whether or not you would actually want to do something like this in particular to say, well, send to either S gateway regardless. And on failure, do not use S gateway 1 and 2. So we're kind of arbitrarily making the green S gateways unavailable for S8 interface. Or it could even be that they don't support S8, right? I just said arbitrarily, but it could be like not necessarily an operator decision. It might be a limitation of this particular S gateway. It just doesn't support S8, which could be. So P gateway requirements, basically the same. Load balance, P gateway 1 and 2 in local. On failure, load balance to P gateway 1 and 2 in remote. If that fails, use P gateway in local. If that fails, use P gateway 3 in remote. So you get the idea. You prefer the greens in your own region. If that fails, take the greens in the remote region. If that fails, take the yellows in your region. If that fails, take the yellows in the outside region. S8, load balance between the P gateways in either region. And P gateway, just P gateway 3s, only 3s. And then finally, some added bonuses, or to add a little bit of complexity to it, all P gateways must support GGSN co-location, so they have to support the GN or GP interfaces for home or roaming respectively. And we're going to say VoIP. This VoIP network, it's only in the West. We only support the APN VoIP for Western P gateways. And the APN VoIP is LTE only with no GPRS access and no roaming access. So VoIP is very limited. So this might be a VoLTE or an IMS type APN, just from its name, probably stands for Voice over IP. And it's only in the West. And that's kind of the scenario. So if we had something like that, we'll go to my MNC 123 file. And this is how we'd kind of approach it. So the tracking area in the West, and I'm using this tracking area number 1, is this tracking area number. So in tracking area number 1, I'm going to say that, and you sort of follow service by service is how I would read this. So let's just break it up here. So just by service, so it's a little bit more readable. And again, it's hard for me to tell when I'm doing this video as to how readable it's going to be or how readable the text is going to be. But these first 6 records, these first 6 NAPTR statements are all for S5. They're advertising the S5 ability of these 6 S gateways in the West and in the East. And here I've set top on for them. That means topological closeness matters when I do my calculation for what S gateways I should select and what P gateways I should select for them. And we're going to get to that in a second. Next, notice my order statements, 10s, 20s, 30, 40. So prefer the first 2 statements, and again, this is tracking areas only in the West. Prefer the Western S gateways, which are green. Second order statement, prefer my East S gateways, which are green. Third is take the yellow S gateway in the West. Fourth is the yellow S gateway in the East. So I'm kind of accomplishing that requirement earlier where I say prefer the greens in your local, then prefer the greens remote, then prefer the yellows local, then prefer the yellows remote. And I'm doing that with these order statements. The 10s and the 20s are for the pairings of greens, active, active. And I'm defining just the interfaces for those S gateways. And this is just for S5. Meanwhile, for S8, we said that we wanted S8 to prefer the yellow and only the yellows, and to load balance. So I don't want to order them in terms of preference. So I'm just going to take S gateway 3 in West or East regardless, which again may or may not be practical. You can see clearly how you could change that if you wanted to change priorities. But I'm saying take the West if you're a Western tracking area. No, I'm saying if you're a Western tracking area, take either. That's how this is written, these 2 order statements. And it would load balance between these 2. That's the idea. And I'm saying I don't care about topological closeness, so I'm doing top off. And we're going to see the importance of top on in a second. So when we talk about the APNs and how they're going to map to the right P gateways, because again, P gateways don't map to the tracking area. They do not map to location. They map to the APN. So this Internet APN, we are defining, and again, I'm going to sort of separate S5 and S8. S5, S8, GN, and GP. So for the S5s, I'm going to say West greens is my first, and then East greens is my second, right? And then West and East yellows are being used for roaming. And you'll notice here that there's nothing in order statements. This is kind of a key point. There's nothing in my order statements which say West is first and East is second, right? But since I was talking about West, I put it that way, but what makes that so, you might ask? And why can't I do it that way? And the reason is this APN is an APN record agnostic to tracking area, right? I'm not able to tie an APN necessarily to a geographical region by a tracking area number as I can an S gateway, because this P gateway can potentially serve this Internet APN anywhere in your PLMN. So I can't say West is better than East because that record would not work very well for my Eastern implementation. So instead what I'm saying is these are all equal from a NAPTR order perspective. So consider them all when you're doing your calculation, but the top is on. So care about topological closeness, which means my west and easts are equal at this level, but when I consider, if I'm an MME and I've got my S gateway records and my P gateway records, top is on, so I care about topological closeness. I've got two wests and I've got two easts, which are otherwise equal, but down here my tracking area statements are also saying top on, and I have decided that west is preferred over east if I'm in a western tracking area. So my wests come first. And this actually takes precedence over the NAPTR order statements, incidentally. So 3GPP defines a hierarchy for it. So first, prefer the difference between co-location versus not for GN and GP. If that's not a factor, prefer the difference between topological closeness versus not if top on is on. And then if those tie, consider these order and preference statements. So that's the hierarchy. So I'm saying top is on. So consider topological closeness before you consider anything else. So order 10, this first lowest order, is west green for tracking area 1. So if I'm in tracking area 1 and I'm requesting the Internet APN, I care about west green before I care about east green because the topological closeness indicator is on. And it's only if those were to fail that I would take what is eligible, which is east green, and vice versa in the eastern regions because I've reversed the order statements in this TAC in the east. That's tracking area 257, I believe, 101 hexadecimal. This tracking area, I've said that east green is preferred first, then west by these order statements. And for P gateway, I care about topological closeness, so I'm going to match the greens before I match, so I'm going to match the greens, and I'm going to say within green, my west is closer than the east. And just to be clear, when I say topological closeness, what I mean is that they'll go from right to left in DNS hierarchy and go for the longest match. So if I've chosen this east green S gateway, sgw01.east.green, well, going from right to left, the P gateway that matches that would start at green, and then it would be east. East is a longer match than west. So I would prefer my east P gateway to map because my S gateway selected first is the east S gateway. So that's how the two can kind of pair together. So to go back quickly to my scenario, have I met those requirements? So load balance the two S gateways and local on failure, and I did this all with the order statements, right? So I'm going to say that's relatively check mark. Order 10, 20, 30, and 40 respectively. And S8, I simply only defined S8 interface as being on S gateway 3, I believe. Let's go back here. S8 is done, right? So I said load balance S8 and S8 on both sides, and that's done. MMEs I've done equal. I didn't define any requirements actually for this scenario for MMEs being of any particular type. Typical to load balance, you don't really care about topological closeness for MMEs. And for this VoIP APN, I'm really just removing stuff from its requirements. I'm just saying only to advertise S5 and only support it in West. So you see it's just got the two West P gateways. What I did not do here is add records for yellow, but you can see how I could, right? So the scenario here is not meant to be complete as I've illustrated it. It's really just meant to say how you would approach these order statements to prefer one P gateway or another, how you would use topological closeness versus not. These order statements, again, the priority matters. It's if you care about GN versus GP versus not, then you will take a P gateway that supports GN before one that doesn't as your very first level of consideration. That's co-location. If co-location isn't a factor, you take the difference between top on and top off, and in which case you do your recursive check on the full DNS hierarchy from right to left on which is closer, and prefer the P gateways closer versus further in terms of that level of topology, which is incidentally why I put green further right than west, right? Because otherwise I'd be matching my wests first, so my west yellow would beat my, if you remember I said the greens even far away should match before my yellows that are local. So with top on I had to put green further right than my west and east. That's why I did that. That again is kind of how you're going to need to tweak your DNS config to match different specific requirements. Like if the requirement was the opposite, if the requirement was that I have to map, oh, what happened to my, here we go. If my requirement was that my second option, if all my P gateways in the west were gone that were green, was to take the yellow in west, then I would need to kind of rethink this config file a bit, and I might decide that green is inside and west is further to the right, just to make the top line work as I would expect it to. But this gives you the idea. Yeah, and the other records here, I'm using the aliases again. And you can see if I had 100 tracking areas, how much less typing it is to add this one little statement than to add these 12 lines and to maintain them all the time, right? And then again, my node records for the P gateways and the MME definitions and the interface IPs. Those are really the types that you're going to need for the config file. So this is enough, I would say, to at least get you started if you're trying to configure DNS for the EPC and understand basically what's going on when we look at EPC DNS records. So I want to talk a bit about IMS. DNS is used in IMS for completely different, just completely different things. Used to resolve information on SIP transport layer. I should say this last part of this video, I'm going to sort of leap into the IMS world. So we're not talking about the evolved packet system right now. So we're done with EPS essentially for this discussion. Talking about DNS in the IP multimedia subsystem, where we care about SIP as the main protocol, and we're talking about telephony, voice over IP. So we use DNS to resolve information about SIP's transport layer. For those familiar, basically the SIP protocol wasn't really rigged to a particular type of transport, so it can use UDP, it can use TCP, it can use SCTP. In fact, within one stateful dialogue for SIP between two systems, you can have it potentially switching on the fly between UDP and TCP. So there's a need to learn in some situations. If you only know the name of a server, you need to know what transport layer it supports, if it supports UDP, if it's UDP and TCP, if it prefers SCTP, how to reach, so it's sort of beyond the IP address. You also potentially have a need to know weighted information, like do I prioritize 1 versus 2? Do I send 70% of my traffic to gateway 1 versus gateway 2? That's going to be resolvable. It's used to get IP information when names of servers are learned. SIP headers often will refer to names and URIs rather than IP addresses. So to resolve an IP from a URI, that's something that you would use DNS for. Enum is something special. So for telephone numbers, if you want to get a SIP URI or any type of URI really for a telephone number, there's a standardized method of doing that called enum. And I'm going to kind of reference that here. So I'll go into a DNS config file for IMS and go over some scenarios. You'll notice that the IMS domain name hierarchy is also standardized, and it uses the same 3GPPnetwork.org kind of notation as the EPC does. So I'm going to go into this file, and there's another one that I'm going to go into after this. So again, the same kind of base DNS zone config as in the earlier examples. Here I'm going to use a NAPTR record for a different type of purpose. This is kind of a triplet here. I call it a triplet because you get 3 different types of records that are 1, 2, 3 punches, one after the other. So let's say that I have an MMTEL application server in my IMS network, which is, MMTEL refers to Multimedia Telephony Application Server. It's a 3GPP standardized term. It's basically the telephone switch or the telephony brain of IMS. And I want to learn about an MMTEL application server named MMTEL-AS. Well, I would send, if I'm, let's say, a serving CSCF, if I want to know about this application server, I might send a network authority pointer or a NAPTR query to a DNS server and basically say, what services does this MMTEL-AS support? Same type of question, by the way, as what the MME would have been querying for a P gateway or what it would be querying for an S gateway from APN names and tracking areas. Here I'm asking for the server by name, and I'm getting different types of answers. So you see some things similar. You see this order statement, which again is priority, just as it was in the EPC case. But here you see the flag is S, as opposed to an A, and the service is a bit of a different notation. It's not that X3GPP-GTP whatever. You're saying SIP plus D2T, which is also standardized. That refers to the service of TCP transport for SIP. And this S flag says that instead of an A record, what's coming after this is an SRV service record. And then this redirect statement, so when I was kind of simplified it a bit before by calling it an interface, this is a redirect to the service record, this S flag, of SIP TCP.mmtlis. So if you want to learn about its TCP transport, then redirect to an S or an SRV type record called this. That's kind of how you would read this NAPTR statement. That's your first thing. And its lower preference is to use UDP, indicated by this order statement. And UDP is available via this redirect. So this, there's going to be an SRV record for this statement. Now, if I were to change this, I could actually change this to an A flag, and I could make this an interface like, let's say, f0.mmtlas. So now it just says, if you want to know about its UDP information, just query for the IP address of eth0 on mmtlas. So that's a different type of answer, and we get a different type of subsequent request. So if I was to look up this A record for eth0, I would just get an IP address. Whereas with this S record, I know to ask for an SRV record type after this NAPTR query and to get different information, more flexible. Basically, if I have an S record after the NAPTR, I can convey more detailed information than an A record. It's not just an IP address. I can give all the information you see actually right here. So if I care about TCP, which I said that I did because my NAPTR query said that I prefer it, I prefer TCP, so if I prefer TCP, I can go down here and see what can serve TCP for this application server. And you see that I have 2 records for TCP. And I have, in this case, equal priority, so I want to use both of them. It's not active standby. I want to use both, and I want to send 80% of my TCP-based traffic towards ETH1 as an interface. And I want to send 20% of my traffic to ETH2 as an interface, and by the way, I'm using SIP default standard port 5060. So what an SRV record really does is it lets you define weights, priorities per interface for a service, not just define different services to different gateways or different services to different SIP servers. I can define, even for one SIP server, I can define multiple interfaces, say what their priority should be if I'm going to select this particular application server, and if I'm going to do that, I can say I can basically set thresholds to say what amount of traffic I send to what, or how often I select for different transactions which of these 2 server interfaces. So it's just more flexible basically as an SRV record, and it's going to map to an IP address from this target statement. So this eth1.mmtel-as, it presumably has an IP address. SRVs will be followed by an A record, and then here I have the A records defined for ETH1 and ETH2. So this triplet is very common when you're defining an application server, or really any SIP server or SIP proxy in IMS in the way that you would define them. There's other well-known service. There's a service name for SCTP. There's a service name for SIP-S. So this example I use TCP and UDP, but that's not at all exclusive or all-encompassing. Here I defined a serving CSCF in an IMS network. So this is serving CSCF1. And this is just giving another example of doing much the same thing, defining different services and what SRV records are applicable for them. So I'm saying, in this case, prefer D2S. D2S is going to be down here. D2S, where did I put D? D2S should be SCTP. So I said SCTP.SCSF, that's this first record, right. So I've got 2 interfaces that can serve this first NAPTR answer, this SCTP. And they're going to be ETH1-100 and ETH2-100 on SCTP port 5060. And here at the bottom, I've indicated a non-default. Actually, no, sorry, that's the default for SCTP-S, and that's probably what this is. Yes, that's what it is. Sorry, I wrote this a few days ago. I'm just recalling it as I read. So SIP-S is for SIP Secure, and it's using the SIP Secure port 5061. So this is all pretty standard stuff, but really it could be different is my point. Like if I wanted to make these weights different, if I wanted to change priorities, like if I had 2 interfaces within a single protocol, so I prefer TCP, but within TCP I prefer one, and if one's down, use port 2, I could use priorities for that. and then weights, again, percentage to load balance equally or unequally between different interfaces if they're equal priority. Right, so it is quite flexible. Next, I just wanted to end this with an entirely different example of use of DNS, which is for enum. And here's just a couple of example telephone numbers that one could define using enum in DNS. Use case for this is, let's say I needed to route to a given phone number, and I wanted to decide, is this a SIP capable phone or not? Like, do I have to route this to the PSTN, or can I route this to a SIP peer? Right? That's kind of what you want to know, because if it's SIP, then you've got more flexibility. You could potentially make this a video call, etc., etc. So an enum query will be done by different systems at different situations, like an SCSCF or a BGCF or an ICSCF, depending on your implementation, your particular IMS design, can potentially have a need to query enum. For those in the telecom side not familiar with enum, it's kind of like number portability 2.0 or number portability in a VoIP scenario. That's kind of what it is. And here we're using, again, network authority pointers in a completely different way. So this is just to illustrate how flexible network authority pointer records are. So here I'm saying, and again, right to left, so ARPA E164, this is a standard DNS level of hierarchy for telephone numbers. E164 is the number plan. So this would essentially be an MSISDN if it's a mobile subscriber. And this is 1 NPA of 234, and then NXX of 555, just like the movies. I didn't want to use a real phone number, so 555 NXX. And 4 digits afterwards. I'm saying that phone number, if you're querying me for that phone number, if you want to know if it's a SIP subscriber or not, essentially, and if it's a SIP subscriber, how you route to this particular SIP, or I should say what gateway you should route to reach the operator that owns this phone number, then you've got two records. One of them is for SIP, the other one is for email. And I use this because it's an RFC example, actually, but just to illustrate that it's not just, enum is not just telephony strictly. It pretty much is, but not just necessarily. And you see a regex expression, and this is a little bit hard to read, but it's not too bad. So I'm going to break it down here. So this might look like gobbledygook, but I'm going to space that out just a bit to sort of explain what's going on. So first of all, this is a read and replace statement. If you see this regexp, it's read it as a read, the first statement, and replace it with the second statement. So I'm querying for a phone number. Well, take whatever it was you were looking for, which should be a phone number if it's an enum query specifically for the purpose of telephony, in which case, as the RFC would say, you have an application-specific number, or an application-specific value, which in the context of telephony enum is always going to be your phone number in international format, so starting with a plus. So if I'm looking for a phone number, then replace that with a SIP URI is what this statement is doing. And it's using what's called regular expressions. So this is a little bit more theory than I would want to kind of just throw at you at the end of this video. But I'll go through it very quickly. This is the regular expression form. What I'm saying is this exclamation point is a delimiter, first of all. So the beginning of the regex statement, then I'm making the read statement. The exclamation point is another delimiter, so everything after it is the replace statement, read and replace. So read this statement. This statement is enclosed in brackets just because I needed to escape it for the way that bind configuration is going to read this file. This hat means starts with, so if your application specific value, which in the case of enum is again a telephone number, if it begins with, and here is an escaped plus sign, so if it begins with plus 1, 2, 3, 4, 5, 5, 5, 6, 7, 8, 9, and ends after the 9, so I'm matching only that phone number and nothing else. So if you're requesting that phone number exactly, then replace that with this SIP URI. And the SIP URI format will accept the regex replace of 1 or /1, where this first slash is an escape. So 1 is really the phone number, that which you read. So replace that which you read with the characters SIP : that which you read, followed by @example.com. End. So it's written to be quite flexible. It is a little bit complicated. To be honest, what you're probably going to do is write it once, make it work once, and rinse and replace for everything you're going to add to it. You kind of only need to do it. It's not something you're going to play with very often, the format of it. You're going to kind of fix on a format that works, and you're going to probably just keep it. But this is kind of just so you understand that, I guess. If you're looking at this and just from not knowing anything else about it, it looks really like gobbledygook, like it's really unnecessarily complicated, but it's really just unnecessarily flexible. So I could, for example, reduce this and say if you're looking for any number that starts with 1, 2, 3, 4, if I want to target that NPA, then send it to a URI which maps to a gateway that serves nothing but that NPA. You could do that. At the same time, if I'm looking for an email address and that request is really for a mail to, then I get a URI of mail2:johnsmith@example.com. So if I wanted an email address from this phone number, I can do it. If I wanted to not speak SIP, but if I wanted to speak H323, there's a standard way to write that. And you'll see that this U flag, just to end this, this U flag, similar to how you had an S and an A, this U flag makes, again, the treatment of this record means something completely different. This U flag is going to say read and replace the regex statement, which has, again, just nothing to do with any of the other scenarios we've used DNS for. So that is pretty much everything that I wanted to cover in this video. I know I've thrown a lot of different theory at you in terms of, but it's all DNS, right? So this is all how you would manage config files for DNS to do practical things in the evolved packet system and in an IMS context, and I gave that example as well. All of these are somewhat complicated in their own right. There are design decisions to be made in their own right, but this is how you would kind of, I guess my hope of this video is that I've given enough examples for you to be able to take what you're trying to do with DNS and be able to kind of put in take this in that context and kind of apply this to help configure whatever it is you're trying to configure in DNS to make these very different use cases of DNS work. So thank you very much for watching this. This has been a longer video than I expected it to be. I'm probably going to cut it up in two, but I hope this was useful for you. Thank you very much for watching.